Hi there once again, and we'll be doing another sample problem for this topic in load analysis. Okay, so this problem is taken from the textbook of Hibbler, Engineering Statics, and this is specifically problem 6-106. Now, the problem says that the bucket of the backhoe and its contents have a weight of 1,200 pounds and a center of gravity at G. Determine the forces of the hydraulic cylinder AB and in links AC and AD in order to hold the load in the position shown. Okay, so that means that even though this is a mechanical systems and it is actually moving, but in this instant or in this position of all the parts connected together, what's gonna be the forces in some components? Okay, so we have here the backhoe. This is the assembly, and we have here the hydraulic cylinder. Okay, so this hydraulic cylinder is actually either pushing this, or let's say pushing or pulling, or also this one, this cylinder AB. So if it pulls like this, then this bucket will rotate. Okay, so this is the main picture. Okay, and it says here that the weight, so we have the weight here of the load, let's say the gravels, so the load plus the weight of the bucket itself is, it says here 1,200 pounds. Okay, and it is acting at G. Okay, and we are asked to find the forces in AB, in this hydraulic cylinder AB, and the links AC and the link AD. Right, so if we try to zoom this in, what we'll see is this one. Okay, so here is our bucket. So this is one assembly, and this bucket or this assembly is connected to other parts or other sub-assemblies. So this is the link AC, so AC, and then the link AD, and this cylinder, hydraulic cylinder AB. So we are asked to find what is the internal force in this link, and in this hydraulic cylinder. Okay, so first we'll start with the bucket, because we have the loads given here in this assembly, in this bucket. So if we have these external loads, then somehow we can get the support reactions, and then we can work our way, or I mean, when we find the support reactions, then we can transfer those support reactions to the other components. All right. So the plan of the problem is that if we have this exploded view, so we'll start with this bucket. So this bucket is actually supported by something like an internal pin, or it's actually a moment release. Or we can just draw, if we are more convenient with this, we can just draw the pin. Okay, but this is actually this is a moment release, because there's no moment reactions here. Okay, so if we have a pin right here, and we have a link, and recall that a link has a support reactions that is parallel to the direction of the link itself. So this is our link, so the support reactions would be in this direction. Okay, however, I've also said that this is also you can express this resultant in terms of the X and Y components, so therefore this is also something like a moment release, or it's actually a moment release. Okay, so once we've done once we've applied the equilibrium equations in this assembly, then we can, if we can find this force, then we can translate this force to the joint right here. Okay, so if we apply the equilibrium equation at the joint right here, this force will just simply be equal to this force, and this force will be equal to this force. But you would notice that there's going to be a difference in the direction, because with respect to this link, this will be a reaction force. Okay, so it's just a transmission of forces. So once we have this, right, we apply the equilibrium equation in this link AC, and then this is actually equal in magnitude, because this is an equilibrium condition. So this will be equal, except that the direction is different. And then we transmit this force to the joint A. Okay, so you would notice that we apply equilibrium equations to both the parts and the joints. Okay, and then at joint A, then if we apply the equilibrium equations, then we can actually solve for this unknown and this unknown. And this unknown, this is actually the force in the hydraulic cylinder, and this force right here is the force in this link AD. Okay, so it's all about transmission of forces. Okay, so now let's start our computations, and I have already drawn here the free body diagram. So here is our bucket assembly, and we've modeled this as a pin, and this one is a link, supported by a link. So we have this reactions AC. Okay, so you would notice that if you take summation of moment at A or at D, this is D and this is C. If we take summation of moments at D, then we can solve for this unknown. Okay, and take note that this one should be expressed in terms of their components X and Y. By the way, this should be E. This is not point D, but rather this is just E. Okay, so you would notice here, this is C, this is E, and the D is right here. Okay, so this one should also be E. Okay, so the next step is to apply the equilibrium equation. Okay, the equilibrium equation, and take moment at point E. Okay, so summation of moment at E is equal to 0. So let's assume clockwise direction is positive. So this is clockwise, and the force AC, right? So with respect to E, these are all counterclockwise. Okay, so this will be 1,200, right, times the moment arm of 1.5. 1.5 is equal to, right, AC, or I think this should be anyways, this is just simple, so let's just write AC, right, cosine. So I'll take this, I'll take the X component, so AC cosine 60 times the distance, moment arm distance of 1. Okay, so plus AC, the vertical component, AC sine 60 times the perpendicular component of distance, which is the perpendicular distance 0.25. Okay, so if you do the math, what you get is 2,512.19 pounds. Okay, by the way, how did we get this 60 degrees? It's from the given right here. Okay, so this is 120 degrees. So if I take this angle, this will be right, because this one is 30 degrees, so 90 minus 30, this will be 60 degrees. Okay, step 3. Now that we have this force, this is 2512. Right, so this is 2512. So all these are 2512. And now we'll take equilibrium equations at A. So taking equilibrium equations at A, at joint A. Okay, so it's actually like this. Okay, so for the joint A, this is our free body diagram. So we have two unknowns and we have two equilibrium equations. So we have, so we can solve this using summation of forces y and summation of forces x is equal to 0. Okay, so now let's apply the equilibrium equations. Okay, applying now the equilibrium equations. Okay, so summation of forces, this is at joint A. So summation of forces, I think we should start with y. Summation of forces y. Okay, so summation of forces y is equal to 0. So this is, the component is 2512.19 sine 60 is equal to AB sine 45. Okay, so therefore AB is equal to 3076.8 pounds. And then the summation of forces x is equal to 0. So we have this x component, AD, right? So this is the only direction to the right. So AD is equal to all the forces to the left. So this is 2512.19 pounds cosine 60, right, plus the x component of AB. Right, so AB is 3076.8 cosine 45. And this is 3,431.7 pounds. Okay, so these are all our solutions. Okay, so once you have this, values right here, then you can actually solve for the internal forces. So by just making a section cut. So if we cut it right here, then what's going to be the internal forces? Okay, so I think that's all for this problem, and we'll do another problem. this is our fourth sample problem for the topic in load analysis. This one is taken from the textbook of Hibbler, uh, Engineering Statics, and the problem is 6-100. The problem says that the two-member structure is connected at C by a pin which is fixed to BDE and passes through the smooth slot member AC. So here is our structure. It is composed of two members. So one member is this horizontal member, that's the member BDE, and the diagonal member, this is member AC. Now you can see here that the diagonal member has this slot. So this slot in this is where, inside this slot, this is where the pin that is connected to this member BDE is attached. So once this rotates, so somehow it will have some or we can say some play along the axial direction with respect to this member AC. So to me, I describe this as an axial release. Okay, so for a slot, it's an axial release, or typically we describe it as something like an internal roller. Except that I think it is more precise to describe this as an axial release, because it allows movement in the axial direction with respect to this diagonal member. Okay, so it says that we are to determine the horizontal and vertical components of reaction at the supports. So right here, this is a pin support, this one is a roller support, and this one is a pin support. Now, although the problem says that we are only to find the components of the reactions, I'd like to draw the internal force diagram for each of the member. So if this member is experiencing, let's say, axial or shear and moment, then we have to draw that. Okay, so for the solution, so the first step is to draw the free body diagram, which I have already drawn right here to save time. So here is our structure, and right here we have an internal roller or axial release right here. So first we can draw the free body diagram of the entire structure. Okay, so right here we have the X and Y components of the support reactions, and right here we only have the vertical reactions because it's a roller support, and for the pin support we have the X and Y reactions, and plus the given loads or external loads, that is 500 pounds right here at point this is point B, and we have here a given external moments, that is 600 pounds. Okay, and the distance is also given. Okay, so that is our figure 1. And for the next figure, we just isolate the member 1 or the member AC, and then draw the free body diagram. So for this, since this is a roller support or axial release, for a roller, it's actually perpendicular to the direction. So it is represented only by this single force, but of course we all know that any force that is not purely along X and Y can also be translated in terms of X and Y. And the same is also true for the support reactions. Even though this is AX and AY, we can represent that in terms of a resultant force. Okay, so right here, the vertical distance from point A to point C is 4 feet, and the horizontal distance is 3 feet. So we need to solve for the angle right here, so that we can determine this one. Okay, so it's just a simple trigonometry, and the value can be found just simply by the inverse tangent of 4 divided by 3. This is 53.13 degrees. Okay, so this 53.13 is the angle right here, and it is the same as the angle right here. Okay, so that is our figure 2. And the next is to isolate the member BDE. So here is it. So right here, the forces are the external 500 pounds and the support reactions at D and E, and the support reactions of the internal joint. So with respect to this member, the force reaction is along this direction, but with respect to this member, it will be along the opposite direction. Okay, so the first or the second step is to apply the equilibrium equations, okay, in figure 2. Okay, so right here we cannot use this much, for now, because we have 1 2 3 4 5, so we have 5 unknowns right here, and we only have 3 equilibrium equations, so we can't use that. But using this one, using this figure, if we take summation of moment at A, then we can solve for C, and we take summation of forces in the x and y direction, then we can solve for our unknowns. Okay, and then we translate the unknown, the value of the C, to this figure, right? So if you have the value of C, you only have what's left are 3 unknowns, dy, ey, and ex. So when you apply the equilibrium equations, then you can solve for that. Okay, so let's start with figure number 2. So let's take summation of moment at A is equal to 0, and our assumption is clockwise is positive. Okay, so let's take moments right here. Okay, summation of moment at A. Okay, so all the moments and the forces that causes rotations, we have to take that into account. So right here you have the unknowns. The only unknowns is C and the perpendicular distance. Since this is 3, this is 4, then this one would be 5 feet. Okay, so this will be C. Okay, C times 5, right, is equal to the forces or the moments that causes clockwise rotations. So this is 600 pounds. So therefore C is just equal to 120. This is pound foot. So our value of C is just 120 pounds. Okay, so if we have C, then to solve for AX and AY, we need to translate this, or we need to convert this in terms of its X and Y components. Right, so CX is just simply equal to C sine theta. Okay, so why is it sine theta? It's simply because this is opposite over hypotenuse. So the reference angle is based on the y-axis, so the x would be sine theta. Okay, and this one is equal to 96 pounds. Right, now for the cy, this is c cosine theta, and this is 72 pounds. Okay, next is, let's take summation of forces x is equal to 0. So AX is just equal to the x component. So AX is just equal to CX equal to 96 pounds, and AY, or if we take summation of forces y is equal to 0. So AY is AY plus, alright, so AY is upward direction. Our assumption for C, or the solve value for C, is upward direction. So AY plus C is equal to 0, and this will be AY is equal to negative 72 pounds. So therefore AY is equal to 72 pounds, but the direction should be downward. So instead of this upward direction, the AY value is downward. Okay, so that makes sense because this one is upward, this one should be downward. Okay, the next step is to applying equilibrium equation in figure 3. Okay, so let's take summation of moment. Okay, summation of moment. So let's take summation of moment at D, or at E. I think at E. So if you take summation of moment at E, and by the way, this must be expressed in terms of components. So the vertical component is this is 72 pounds, and the x component is 96. Okay, so summation of moment at E is equal to 0. So first is EY, right? EY, okay, this force times the moment arm of 2, right? So this is, oh sorry, this should be dy. Okay, so we are taking moments at E, so dy, this is clockwise, dy times the moment arm of 2, right? Dy times 2 is equal to, this vertical component is counterclockwise, this 500 pound is also counterclockwise, right? So dy is equal to 2, dy times this is equal to 500 times, right? 500, what's the distance? 3 plus 3 plus 2, that's 8, right? Plus cy times 5, right? So cy, the 72 pounds, okay, the moment arm is 5, so cy, what else? The value of cy is 72 pounds, so dy is equal to 2,180 pounds. Okay, so the next is, let's take summation of forces y is equal to 0. So the forces are dy, ey, 500, and this 72 pounds. Okay, so E sub y plus, right, so E sub y plus this d is equal to 500 plus 72, right? So ey is equal to, it says here ey is equal to negative 1,608 pounds. So that means that ey is 1,608 pounds, but the direction is downward. Okay, and then last step is summation of forces x equal to 0, and cx is just simply equal to ex equal to 96 pounds. Okay, so the next step should be, in your homework you should provide a summary of the equations, the magnitude and the direction of the support reactions. Okay, but since we don't have much time right here, then I'll just we'll just forward this to the internal force. Okay, so even though the problem didn't ask us to find the internal force diagram, but right here we'll be doing this because this will be the basis of the stress computations. Okay, so recall that in this point A we have the cx and cy. I mean, this is ax and ay, right? But you can actually translate that, or you can take the resultant, and what you will get is actually 120 pounds, which is perpendicular to this longitudinal axis. Okay, so you can do that computation. You can check this this angle right here, right? So the equation is r is equal to let's say the 96 squared plus 72 squared, right? This is 120 pounds. And you can also check the theta, right, which is just the inverse tangent of the ry all over rx, which is just 36 point something. Okay, so this one, the equivalent of the ax and ay is perpendicular to this longitudinal axis. Okay, so with respect to this member, our forces would be 120 downward, right? If this is our translated, let's say this is our translated the translated coordinate systems. This is x, this is y. Okay, so this is downward, and our support reactions, this is c. Okay, so this is 120 pounds, and we have the externally applied moments of 600 pounds. Okay, so with that, we can draw the shear and moment diagram. So if we start in this point A, we go downward, and then it's constant all throughout, and then we go upward. The value is negative 120. Okay, and then for the moment, then you can just do the shear and moment diagrams, and you'll see that the diagram looks like this. And because we have a concentrated moment, so this will produce a jump, right? So 600 pound foot, and it's 0 right here. And of course, there's also no actual force. Why? It's because as I've said, this is an actual release because it can move freely, so there is no actual forces acting on this member. But with respect to this horizontal member, so this is our C reactions, and as I've said, we can convert this or express this in terms of its components, because we have a support reactions along this longitudinal axis. Let's say this is our x and this is our y. So we have 96 right here. So there must be some force that's resisting it, or along the opposite direction, so that it can be in equilibrium. Okay, so we have this concentrated. We have concentrated loads in x and y, and the vertical reactions. So in terms of axial, so if we start at point A, right? At point A, there's no axial force, but then at point, I think this is at point C. Sorry, this is point B. So from point B, right, there's no axial, but from point C, because of the horizontal component, then there exists an axial, and it's constant all throughout until it gets to point E, right? So this is negative 96. Now in terms of shear, so we have it downward, okay, and then it's constant all throughout, and because of these vertical components, it goes downward still, okay, and at this point D, it goes upward, and then it closes right here at point E. And in terms of the moment, so we get this diagram. All right, so I think that's all. That's all for now in these problems, and in the next video we'll be doing 3D problems for internal forces, and we'll start doing computations regarding torque or internal torque diagrams. All right, so see you in the next video.